So in this video I'm going to discuss the question thermal and statistical physics which appeared in JEST Physical Sciences 2021 examination. So let's continue with the first problem. The statement is an ideal gas at temperature T is composed of particle of mass m with x component of velocity Vx. The average value of mod of Vx is okay. So because we have to find out the average value of the x component of velocity, so that means here we must have an idea about the Maxwell-Boltzmann probability distribution in one dimension, okay, which is given by the relationship P of Vx or Ux, that is equal to d n Ux divided by n. That's a fraction of gas molecule with their x component of velocity in the range from Ux to Ux plus dux, okay, and that is given by m upon 2 pi kt and its power 1 by 2 and exponential minus m x square upon 2 kt. So let's call this as equation 1, okay. Now we have to find the average value of mod of Vx or Ux, okay, and that is given by this is equal to, from in one dimension the limits of integration they range from minus infinity to infinity, and then mod of Ux and then corresponding probability distribution function P of okay, I wrote it like this, P of Ux, okay, or you can write this to be a function of Ux, it's the same thing, and then dux and then divided by minus infinity to infinity P of Ux d of Ux, okay. So let's call this to be equal to I1 divided by I2, where I1 corresponds to the integral in the numerator and I2 corresponds to integral in the denominator, okay. So with the help of equation 1 and 2, so let's call this as I2, okay, and this equation as equation 2. So with the help of equation 1 we can evaluate the integral I2 directly. I2 is equal to, so this is P of Vx, so I will take the constant term outside, that is m upon 2 pi kt. I am taking it outside, okay, its power 1 by 2, and then inside the bracket from minus infinity to infinity exponential minus m Ux square upon 2 kt. Note that k, it's a Boltzmann constant here, d of Ux, okay. So here we will make use of the result that integral from minus infinity to infinity exponential minus alpha x square dx, where alpha is a constant, that is equal to under root pi by alpha, okay. By making use of this standard result I can write the I2 to be equal to m upon 2 pi kt its power 1 by 2, and then I will make use of this results and multiply by 2 pi kt upon m and its power 1 by 2, okay. So here alpha in this integral, alpha is equal to m upon 2 kt, alpha Ux square, okay. So therefore this is nothing but this is equal to unity, okay. So now we have to calculate the value of I1 by following the same procedure, okay. So let's see how we can do that. So let's call this as equation 3. Now to evaluate I1 is equal to, I1 is from minus infinity to infinity mod of Ux and then this quantity, okay. But here because of the mod of Ux here, so what I'm going to do is I'm going to write it like this, 0 to infinity 2 times, okay, because otherwise this integral will vanish if we retain the limits from minus infinity to infinity, okay. So 2 times 0 to infinity and then Ux and then P of Ux, so with the constant terms m upon 2 pi kt power 1 by 2 and then exponential minus m ux square upon 2 kt d of ux. Okay, so I will take the constant terms outside. So 2 into m upon 2 pi kt power 1 by 2 0 to infinity ux exponential minus m of ux square upon 2 kt d of ux. Okay, so here we will make use of the standard results, which is 0 to infinity x exponential minus alpha x square dx, that is equal to 1 upon 2 alpha, where alpha is equal to m by 2 kt here in this integral. So these two results, they imply that I1 is equal to 2 times m upon 2 pi kt, its power 1 by 2, and then 1 by 2 alpha, 1 by 2, and alpha is m upon 2 kt, so that is m upon 2 kt, and this upon solving gives us that this is equal to 2 kt, this will cancel with 2 kt upon pi m under root. So therefore mod of ux, that's nothing but I1 upon I2, where I2 is equal to 1, so therefore mod of ux, that is nothing but I1, which is equal to 2 kt upon pi m, so that is 2 kt upon pi m. So I think 2 kt, no, it should be pi here, not 2 here. Okay, in the option D it should be pi, so therefore option D is the correct one here. So let's continue with the next problem. The statement is, consider a system consisting of 3 non-degenerate energy levels with energy 0, E and 2E. Okay, so and these are non-degenerate energy states. Okay, in the limit of infinite temperature, that is T approaches infinity, the probability of finding a particle in the ground state is given by. Okay, so let's first draw the energy level. So we are having a system with 3 energy level with energy 0, E and 2E. Okay, now we have to find the probability that system will exist in the ground states, and for that purpose we first of all we must have an idea about the partition function. The partition function for this system is given by, so here it's also given that G it's 1, all these states these are non-degenerate. Okay, and then because all these states they are non-degenerate, so I can omit G, writing G here, so exponential minus beta ei. Okay, so the partition function is exponential minus beta into 0 plus exponential minus beta into e plus exponential minus beta into 2e. Okay, so that is equal to 1 plus exponential minus beta e plus exponential minus 2 beta e. That's the partition function. So let's call this as equation 1. Okay, now the corresponding probability, that is probability that system will exist in the ground state, is equal to 0, that is equal to exponential minus beta into 0 divided by q, or 1 plus exponential minus beta e plus exponential minus 2 beta e, and that is equal to 1 divided by 1 plus exponential minus e by kt plus exponential minus 2e by kt. Okay, that's the probability that system will exist in the ground states. Let's call this as equation 2. Now in the limit t, when t approaches infinity, that's a very large value. So in that approximation, the exponent of the exponential term, that is e by kt, that will approach to 0, and also minus 2e by kt, that will also approaches 0. Okay, so in this case the corresponding probability the probability that system will be in the ground state, that is equal to 1 divided by 1 plus 1 plus 1, and that is equal to 1 by 3. So therefore C is the correct option here. Okay. Let's continue with next problem. The statement is the free energy density of a gas at a constant temperature is given by F of rho is equal to C rho ln rho by rho naught. Okay, so let's first write the expression for the free energy density, which is F as a function of rho, that is equal to C rho ln rho by rho naught. Okay, let's call this as equation 1, where rho represents the density of gas. That it's given that rho, that is equal to the density of the gas, that's N by B. Okay, while C and rho naught are positive constant. Okay, well, C and rho naught, these are two constant quantities. Okay, these are constant quantities. The pressure of the system is, so see, it's the free energy density, not the free energy. So what we can obtain the final result with the help of the Helmholtz free energy, the expression for the Helmholtz free energy, that's dF, that is equal to minus S dt minus P dV. Okay, from here we can write the pressure as P, that is equal to minus dF by dB. But remember, it's the free energy, not the free energy density, by keeping temperature constant. Let's say this is equation 3. Okay, now from the free energy density we can obtain the free energy as free energy F, that is equal to volume multiplied by the free energy density. So okay, so that will give you the free energy, and this is equal to C B rho multiplied by ln rho by rho naught. Okay, and then by replacing rho with the N by V, that's a density. Okay, that is C B into N by V. Now I'm replacing rho with N by V, and then ln N upon B rho naught. Okay, so this B will cancel with V, so ultimately we obtain the free energy as C N ln N upon B rho naught. Okay, so let's call this as equation 4. Okay, now with the help of equation 3 and 4, now 3 and 4 implies that P, that is equal to P is equal to minus dF by dB by keeping temperature constant, and that is equal to dF by dB, so minus Cn outside. Okay, this one, and now the differential of logarithmic term with respect to V, so that will give you into V rho naught upon M, and then again differential of the term inside the brackets with respect to V, so that will give you minus N upon rho naught into 1 upon V square. Okay, so this N by rho naught, it will cancel with N by rho naught, and 1 of the V will cancel with 1 of the V, so ultimately we are left with pressure, that is equal to C N upon V, and that is equal to C rho. Okay, so therefore actually this is not C like this, so this should be like C and multiply by rho. Okay, so therefore option A is the correct option here. Okay, so let's continue with next problem. The statement is m gram of water at temperature Ta is adiabatically mixed with an equal mass of water at temperature Tb, keeping the pressure constant. Find the change in entropy of the system. Okay, and the specific heat of water is given as Cp. Okay, so let's try to represent the problem schematically. So here we are having a system, one system having m gram of water. Okay, let's say we are having m gram here of water at temperature Ta, and corresponding specific heat capacity is Cp. Okay, now this is mixed with equal quantity of water, that is m gram, but now the corresponding temperature is Tb, but the corresponding specific heat is Cp. Okay, now when this water is mixed, so you are getting a common system whose temperature will be somewhere in between Ta and Tb. So let's say the common temperature of the system is T, that is T as a function of Ta and Tb. Okay, and the total mass here we are having 2m, but the corresponding specific heat will be again the same, Cp. So our objective is to calculate the net enthalpy change for the combined system. So let's say for this system the enthalpy change is delta Sa during this process and delta Sb for this process, such that the net enthalpy change delta S, that is equal to delta Sa plus delta Sb. That's a net enthalpy change. Okay, now here we will also make an assumption that, let's say, Ta is greater than Tb, so that after mixing let's say the common temperature is T. Okay, now and because T it's going to be smaller than Ta but larger than Tb. Okay, so therefore because the mixing is taking place adiabatically, so that means there is no heat loss to the surrounding. So delta Q, that is equal to 0, because mixing is taking place adiabatically. This is also an important point to be noticed. Mixing is taking place adiabatically, so that's why delta Q is 0. So that means it's taking place in isolation. So whatever heat lost is taking place in one system, the exactly equal amount of heat will be gained by the second system. So that means heat lost by system A, heat lost is equal to heat gained by system B. Okay, so now what is the heat lost by system A? So that is equal to mass of the water corresponding specific heat mc delta T. Okay, so delta T is initial higher temperature Ta minus final lower temperature, which is T. That's the common temperature for the both systems. Okay, that is equal to mCp, now the heat gained, and that is equal to T minus Tb. Notice here we are comparing the absolute value of the heat here. Okay, so it's not like a delta T, we are writing like T final minus T initial all the time. Okay, so for example in heat loss, that is mc, the higher temperature Ta minus lower temperature T. Okay, so m and Cp, that will cancel with each other. So from here we will notice that T is equal to Ta plus Tb by 2, and let's call this as equation 1. Sorry, let's call this as equation 2 and this as equation 1. So now we notice that for both of the system the temperature changes from some initial value to some final value, and the corresponding enthalpy change for the individual system can be calculated as follows. The enthalpy change for system A, that is delta Sa, that is equal to temperature change for system A, it's taking place from Ta to final temperature T, and that is dq upon T, and that is equal to mCp and then Ta to final temperature T and then dt by T, and this is equal to mCp ln T upon Ta. Okay, so this is our equation 3. Similarly, the enthalpy change for system B, that is delta Sb, this is equal to dq upon T when temperature is changing from Tv to T for system B. Okay, by following exactly the procedure, same procedure as above, so this is equal to mCp ln T upon Tb. Okay, so this is equal to, sorry, this is our equation 4. Okay, So now the net enthalpy change according to equation 1, net enthalpy change for the system, that is delta S, that is equal to delta SA plus delta SB, okay, and that is equal to mCp ln T upon Ta plus ln T divided by Tb, and that is equal to mCp ln T square upon Ta Tb. Okay, let's call this as equation 5. Now equation 5 can be further written as delta S, that's the net enthalpy change of the system, delta S, this is equal to mCp ln T square upon Ta Tb. Now substitute the value of T, which is Ta plus Tb by 2, so this is equal to mCp ln Ta plus Tb its square divided by 4 Ta into Tb. Okay, that's the net enthalpy change. But we haven't yet reached in the final form as asked in terms of the options which are given in the statement. So we can rewrite this result as mCp. Now it's merely the mathematical arrangement of all the terms. 4 Ta Tb plus Ta square plus Tb square minus 2 Ta Tb divided by 4 Ta Tb. Okay, if you just take a look at the numerator, it's nothing but it's the expansion of the Ta plus Tb whole square. Okay, so this is further equal to mCp ln, okay, 1 plus, okay, so if we are just considering this term, okay, so that will give us a 1. Okay, now when we are considering the remaining terms in the numerator and the along with the denominator, so that will give us Ta minus Tv its whole square divided by 4 Ta Tb. Okay, so that is the final answer. Okay, so let's see which option matches with the obtained result. Okay, so this is option C. Okay, so option C is the correct one here. So let's continue with the next problem. So the statement is a large box of volume B is fitted with the vertical glass tube of cross-sectional area A. So we are given a glass tube whose cross-section area is A, okay, in which a metal wall of mass M fits exactly. So here it's a metal wall whose mass is given to be small m, and it's a box whose volume is capital B, let's say. Okay, the box contains an ideal gas at pressure which is slightly higher than the atmospheric pressure. Okay, so let's assume that the pressure outside is P and the pressure inside the box, that is slightly higher than this value. Okay, because of the weight of the wall. Okay, if the wall is displaced slightly from the equilibrium, find the angular frequency omega of simple harmonic oscillation. Assume adiabatic behavior during this process, and with the ratio of specific heat gamma, that is equal to Cp by Cv. Okay, so we assume that here let the outside pressure is, let pressure outside it is equal to P. Okay, then the pressure inside the box, pressure inside the box, it's going to be slightly higher than the outside pressure, and it will be slightly larger by this amount mg upon A. Why? see, we are having a ball of mass m, so its weight will act in the vertical downward direction. It's mg. So that's simply it's a force which is acting in the downward direction, and it's acting in the cross-section area A here. The cross-section area A of the tube. So that's why the corresponding force will be corresponding pressure will be, it's a force per unit area. That's mg upon area. Okay. So let's call this as equation 1. Now we assume that here in the in this process we will neglect the volume of the tube here, because the box, it's very large. So we will assume that initial volume of the box, initial volume of box, that is equal to V1 and that is equal to V, let's say. Okay, now let the wall is displaced slightly. So what we can do is we can slightly displace the wall in the downward direction. So let wall is displaced slightly downward, okay, by a certain distance, let's say x. Okay, so that the change in volume, so that it is displaced in the vertical direction. So we can understand this from here. It's a tube, okay, whose cross-section area is A. So when we are moving the wall by a certain distance dx, okay, in the downward direction, or x in the downward direction, the corresponding change in volume, so the change in volume, that is equal to dv, which is equal to a times x. Okay, that's the corresponding change in volume. So let's call this as equation 2. Okay, so when we are slightly displacing the wall from the equilibrium position in the downward direction, now the excess pressure inside the box, so because of this process, the excess pressure inside box, we are calling that as P2. So that will be the P1, the initial pressure, plus delta P, that's a slight change in the pressure. Okay, and the corresponding volume, now because we are moving the ball in the downward direction, so the volume will reduce slightly by an amount delta P. So initial volume was B, now the volume has reduced by a factor of delta B. Okay, where delta V is given by AX by equation 2. So let's call these as equation 3. Okay, now because the process is given to be adiabatic, so that means we can apply the adiabatic equation. So that is, we will apply because process is assumed to be adiabatic. This means P1 B1 power gamma, that is equal to P2 B2 power gamma. Okay, now we will substitute the value of P2 and B2 here. So P2 is P1 plus delta P, and then multiply by B2, that which is B minus delta B power gamma. Okay, so now we will take from the first term, we will take P1 outside, P1, and inside we are left with 1 plus delta P upon P1, and then we will take V outside here, which is B1 basically. You can say B1, initial volume we have taken as B1, and then we will take B1 power gamma outside, and then inside we are left 1 minus delta B upon B1, which is B base in fact power gamma, because B1 is equal to B here. So here, okay, so we can replace it with V also, it doesn't make any difference. Okay, and this is equal to P1 B1 power gamma, and inside the bracket 1 plus delta P upon P1 into 1 minus delta B upon B1 power gamma. Okay, so now from here we notice that we can cancel these terms, so we are left with 1 is equal to, so here we are left with 1, that is equal to 1 plus delta P upon P1, and then we can expand this. So this is equal to 1 minus gamma delta B upon B1, by keeping only the first two terms. Okay, so this can be further written as, so after doing the multiplication we obtain that 1 is equal to 1 equals 1 minus gamma delta B upon B1, okay, and plus delta P upon P1 minus gamma times delta P delta B upon B1 into P1. Okay, so we are neglecting this term because we are neglect it because delta P it's small and delta V it's also small, so their product is going to be very small. Okay, so we can neglect this term. Okay, and then 1 and 1 they will cancel with each other. So after that we notice that from here, from this equation we notice that gamma times delta B upon B1, that is equal to delta P upon P1. So from here we obtain the value of the delta P. So from here I can write delta P, that's the change in pressure, okay, when we are disturbing the wall from the equilibrium position. So delta P is equal to gamma times P1 and then delta B upon B1. Okay, so let's label this equation as equation number. So let me see what number I have already given. So up to 3 I have already given, so let me call this as equation 4. Okay, now the restoring force on the wall, it's proportional to the displacement basically. So the restoring force on the wall, that is, we denote that force as F. Okay, so let this be the restoring force, okay, this F, so that the restoring force F, that is equal to minus A times delta P. Okay, that depends upon the excess pressure. Okay, because once when we are forcing the ball in the downward direction, so then the pressure changes by delta P. Okay, so this restoring force will depend upon this excess pressure here. Okay, and this will be equal to minus gamma times A. Now I am substituting the value of delta P from equation 4. So minus gamma times A P1 upon B1 delta V. So delta V, that's equal to AX. So we can substitute the value of delta V here. So that is equal to minus gamma A P1 upon B1 and then A times X. Okay, or this is equal to minus gamma A square by B1 and then P1 X. Okay, now the acceleration of the wall, so what I can do, I can rewrite this as F, that is equal to minus gamma times A square by B1 P1 X. Okay, so let me call this as equation 5. Now the acceleration of the ball is given by, now the acceleration produced in the wall, that is acceleration is equal to the force divided by its mass. Okay, and the force, it's given by equation 5, and that is equal to acceleration, that is equal to minus gamma A square P1 upon M times B1, but now I am writing it as B because B1 is equal to B as we assumed in the beginning here. Okay, so I am replacing it with V now. Okay, and then multiply by X. So from here, let me call this as equation 6. So equation 6 implies acceleration is proportional to displacement, but with the negative sign indicates that it's directed in the opposite direction. So that means it's a this implies it's the motion of the wall, it is simple harmonic motion. So therefore the corresponding angular frequency, the corresponding frequency of oscillation, so that is omega, that is given by the constant term here. So it's omega square basically. So acceleration in what you call in a simple harmonic motion, we notice that acceleration that is equal to minus omega square x. So that omega square or the omega is equal to gamma a square upon mb and then multiply by p1. So we will substitute the value of p1 here, so and it's under root. So this is equal to gamma a square upon mb, and then the value of p is, it is p1 is p plus mg upon a. So this is our final answer. Okay, and this matches with the option. Let me okay, so gamma a square upon mb and multiply by p plus mg by a. So therefore option D is the correct option here. Okay, so let's continue with the next problem. The statement is 5 distinguishable particles are distributed in energy level E1 and E2. So we are having a system of 5 distinguishable particles, and these particles are distributed in 2 energy level E1 and E2 with degeneracy of 2 and 3. Okay, so here for this case G1 that is equal to 2 and G2 that is equal to 2. Okay, find and the particles are given to be distinguishable. So we are having n is equal to 5 distinguishable particles. Okay, so find the number of microstates with 3 particles in energy level E1. So we have to put n1 is equal to 3 particle in energy level E1, and the corresponding degeneracy G1 is equal to 2, and n2 is equal to 2 particles in energy level E2 with which is having degeneracy of 3. It's 3 here, not 2. G2 that is equal to 3. Okay, so now the corresponding number of microstates, because it's a system of distinguishable particles, so that means we can treat them in the classical statistics. Okay, so the corresponding number of microstates which are labeled as omega mb, that is equal to, the general expression is n factorial and pi I, that's a product, gi power ni upon ni factorial. So we will apply this relationship to calculate the total number of microstates that are accessible to this system. Okay, so this is equal to n factorial, which is n is equal to 5 distinguishable particle, 5 factorial, and then g1 power n1. So g1 power n1 upon n1 factorial multiply by the second term, that is g2 power n2 upon n2 factorial. Okay, so substituting a value of g1, g2 and n1, n2, we obtain omega maxwell, that is equal to 5 factorial into g1, that is 2 power n1, which is 3, 2 power 3 upon n1 factorial, that's 3 factorial, multiply by g2, which is 3 power n2, 2 divided by n2 factorial, which is 2 factorial. Okay, and upon solving this result, we obtain that omega Maxwell Boltzmann is that is 720. So therefore 720 is the right answer here. So let's take a look at the last problem from this examination. The statement is a thin tube of length 1080 mm and uniform cross section is sealed at both ends, okay, and placed horizontally on a table. So as shown here in this figure, okay, at the exact center of the tube is a mercury pellet of length 180 mm. So that's shown here. This is a mercury pellet. Okay, the pressure of the air on both sides of the mercury pellet is P0. So it's given when the tube is lying in the horizontal direction, the pressure is P0 on both sides. Okay. When the tube is held at an angle of 60 degree with respect to vertical, so that means when this tube it is so in this position it is making an angle of 60 degree. Okay, so in this case the length of the air column above and below mercury pellet, it becomes 480 and 420 mm. So that means, so when this tube it's lying at an angle 60 with respect to vertical, so this length of the air column in the upper direction, so let's call this as this length as L1. Okay, and the lower length as L2. So this is L2, this is L2. Okay, and we may call this as part 1 and the lower end as part 2. Okay, assuming the temperature of the system to be constant. Okay, if we assume the temperature, let's say temperature of the system is T, calculate the pressure P0 in mm of Hg. Okay, so this is a very basic problem, so we can solve it as follows. So we'll start with the assumption, the points that are given to us. Okay, the information that is given to us is, so we assume that when tube is lying in the horizontal direction, so then length of these parts, let's say this is L0, then this will be equal in principle when it's lying in the horizontal direction. So this mercury pellet, it will be exactly half a in the tube. Okay, so we can correlate this L0 with L1 and L2, because L1, that is the when tube is at 60 degree with respect to vertical. Okay, then length of upper part, that is equal to L1, and similarly length of lower part, this is equal to L2. Okay, so we can connect this L1 and L2 with the L0, which is the length of any of the part along either side of the mercury pellet. Okay, so that means L0 is the length when tube is lying, length of any part when tube is lying in the horizontal direction. So therefore L0 can be given as L1 plus L2 divided by 2, and L1 and L2 value they are given to us. So L1 is equal to 480 mm, that is 48 centimeter, 48 centimeter plus 42 centimeter, and then divided by 2, and this comes out to be 45 centimeter. So that means L naught is 45 centimeter. So let's call this as our result 1. Okay, now when we are keeping this tube at 60 degree, okay, so then we are assuming that in the upper part of length L1 the pressure is P1. Okay, but the pressure at the lower part it's going to be different, because the mercury pellet, because of its mass and height with respect to the horizontal position, it will exert an additional pressure on the lower air column. Okay, so that's why the pressure in the upper part and the lower part, that's going to be different, and we have to find that new value of the pressure here. Okay, so what we are going to do is, we are going to assume that, so when tube is held at 60 degree, when held at 60 degree with respect to vertical, let P1 be the pressure, in upper part. That is part 1. Okay, and P2 be the pressure in lower part. Okay, so and further it's given that temperature is constant throughout the tube. Okay, so that means we can apply the Boyle's law here, because it's given that it's an idle gas inside the tube. Okay, so we can apply that Boyle's law here, because further as T is constant imply PV is equal to constant. So we will apply this law in the part 1 and part 2 of the tube, before and after it's held vertical respect to the ground. Okay, we can apply Boyle's law here. Okay, so for part 1, so that is for the upper part. Okay, so the P1 B1 that is equal to P2 B2. Okay, or P2 B2 I'm writing. So P2 B2 corresponds to a situation when tube is held in a vertical direction. Okay, so in that case we are assuming the pressure is P1, and then the volume is L1, the length of the this air column, and multiply by cross section area of the tube. So we are assuming that the cross section area of the tube is A. Okay, that is P2 B2, and that is equal to P1 B1, that corresponds to initial condition, which is P0 L0 A. So from here we notice that P1 is equal to P0 L0 upon L1. So let's call this as result 2. Okay, now for the lower, similarly for the lower part, similarly for lower part, that is part 2, we can write PV is equal to constant, or P2 B2 P2 L2 into cross section area. So L2 into A, that will give us the volume, corresponding volume, that is equal to P0 L0 into A. So this implies P2 equals P0 L0 upon L2. Okay, so when tube is held at 60 degree respect to vertical, then the mercury column will be displaced to the lower end of the tube, and as a result the pressure in the lower end will be different from the pressure in the upper end of the tube. And we are assuming that pressure in the lower end, that is at this point, it's which is exerted on the air in the lower part, that is equal to P2, and that P2 can be calculated as follows. Okay, so for that we require to have an idea about how we can resolve the force components here, force exerted by the mercury column. So this line, it corresponds to the tube which is held at 60 degree respect to vertical. Okay, so this is a angle of 60 degree here. Okay, and here we are assuming that it's a mercury pellet, okay, whose weight is directed vertically downward. M is the mass of the mercury, okay, and G is the acceleration due to gravity. Okay, so now this is vertical, and so if we extend this line, okay, so that means this vertical line, it's making an angle of 60 degree. Okay, so that's why this angle will also be 60 degree. So now we can resolve this mg into two components, one mg cos theta along this direction, mg cos of 60 degree, and another one along the other perpendicular component, mg sin theta. Basically we do not require this value mg sin theta here. We are merely interested in the component along the tube direction which is exerting the force on the air column in the lower part. Okay, so this is of our interest. Okay, so therefore we can write I can also call this as the force exerted by the mercury pellet on the lower column of the air. Okay, so this way we can easily calculate the pressure P2, okay, which is equal to P1, okay, P1 plus the additional pressure which is exerted by the mercury column on the air in the lower part, okay, which is equal to the force exerted by the mercury divided by the cross section area. Okay, and this is equal to P1 plus mg cos theta mg cos of 60 divided by cross section area A. Okay, now substituting the value of P2 and P1 from equation 2 and 3 in this equation we obtained, we can write here. So I am continuing the calculation from the previous page. So we can write P2 is equal to P1 plus mg upon A cos 60 degree. Okay, so we will substitute the value of P1 P2 from equation 2 and 3. So this becomes P0 L0 upon L2, that is equal to P0 L0 upon L1 plus mg upon 2a. So I am substituting value of cos 60 here, so mg upon 2a, and this implies from here we obtain P0 L0 1 upon L2 minus 1 upon L1, that is equal to mg upon 2a. Okay, so from here we can calculate the pressure P0 as, that is equal to, it's merely arrangement of the term mg upon 2a L0. Sorry, it's going to be in the denominator. Okay, 1 upon L2 minus 1 upon L1. Okay, please note this is also in the denominator. Okay, so let's call this as equation 4. Now we have to find the P0. Now in the problem it's given that we have to find P0 in terms of height h of the mercury. Okay, so that is, we have to find, it's asked in the question, we have to find P0 in terms of height h of mercury, that is P naught. We can write P naught, that is equal to rho, which is rho if we assume the density of the mercury, g acceleration due to gravity, and h is the height of the mercury column that will exert a pressure P naught. Okay, and also mass of the mercury can be rewritten in terms of the length of the mercury column, cross section area multiplied by the density. Okay, so L, length of the mercury column, it's given to be 18 centimeter or 180 millimeter, or 18 centimeter multiplied by area and rho. Let's call this result as equation 5. Okay, now we are almost at the end of the solution. So now equation 4 and 5 implies that, so we have to substitute the value of P naught and m in this equation, in equation 4, with the help of equation 5. So then we obtained from 4 and 5 implies rho g h, which is P naught. Okay, so we are replacing P naught, the pressure exerted by the mercury column. Okay, rho g h, that is equal to m. Now m is equal to how much? That is 18 into a rho. Okay, so 18 a rho, and then mg. So here m into g divided by 2a, and then L0 multiply by 1 upon L2 minus 1 upon L1. Okay, so from here some of the terms will cancel, and after cancellation, for example, a will cancel with a and rho g will cancel with rho g. So ultimately we are left with, this is equal to 18 centimeter and then 2L0 into 1 upon L2 minus 1 upon L1. Okay, now substituting the value of L1, L2 and L0 that we have already determined, so then we obtain H is equal to 18 divided by 2 into 45. Remember, all this information it is in centimeter. 1 upon L2, which is 42, and minus 1 upon L1, which is 48 centimeter, and this after calculation gives us a value of 67.11 centimeter, or which is equal to 671.1 mm. So therefore the pressure P naught in terms of in the height of the mercury column, that is equal to 671.1 mm of Hg. So this is the initial pressure. So this is our answer.